In this video, we're going to continue our discussion about electric fields, taking up a very powerful method for being able to find the electric field for problems that have a particular type of symmetry. This new law is called Gauss's law, after Carl Friedrich Gauss, who developed the mathematics, the vectors, for which this field is based upon. Any vector field, force field vector, electric field vector, magnetic field vector, water velocity vector, any vector field, that is, any function of space and time where each point in space is a vector, we call a field. Any such field that is a vector can be described completely if you knew just two attributes about it. One is, does it flow? Does it radiate outward from some point? And the second property is, does it circulate? Now, there's a wonderful video on the Mechanical Universe series that talks about electric magnetic fields and how they're related to water fields in hydrology. And the math is a little bit for those who aren't in calculus, but you can kind of ignore the math and watch the video and see how they show graphically this connection between different types of fields. Water is a field that we're more familiar with than electric and magnetism, and it will help you. So the first question, if these are the two questions you got to ask, how does it flow and how does it circulate? What makes electric fields flow? Well, the answer to that is charge. We found when we were doing those field lines that we had a charge here. Let's say that that charge is Q. Then there are field lines that flow out of that in all directions. For instance, maybe like this. That's radial flow. The lines flow outward from this charge. Or if it was a negative charge, they would flow inward. But if you took a point in space, say a point right here, and you thought about a little box around this little point. Let me extend my little red line here. There is nothing that starts and emulates out. There's a line that comes in and leaves, but nothing like here where there were no lines and then all of a sudden lines started flowing outward. This charge creates, in essence, the electric field lines. It creates the electric field. And that's what this is a statement of. Field lines leave or radiate from charges. They radiate outward from positive charges. They radiate inward for negative charge. You can think like a negative charge is like a drain in water. It flows in. And a positive charge is like an outlet, a water faucet. It flows out. And in between, if you don't have either a faucet or a drain, the water is just going around. It's not emulating or being created, coming from someplace. Word created for water, kind of a bad thing, but I think you understand what I mean. For static things, that is, if you're not accelerating these charges, then you'll get non-time varying electric fields. That's electric fields that do not depend on time. And in this case, the question is, what makes them circulate? And the answer to the question is nothing. So you cannot get field lines like that. Not possible. We'll find out later on, for magnetism, magnetic field lines do circulate. This is what they do. But electric field lines do not. They only flow outward like sunlight from the sun. Sunlight doesn't go out and come back into the sun. It flows outward. Electric fields are that away. Now, to describe this flowing type things, we do what is called electric flux. And you remember, flux is from the Latin word for water flow, coming from the Romans when they were building aqueducts. So I want to go back and I want to look at some things from the chapter on fluids. I want to remind you some things. You remember that we were looking at volumes. For instance, say some sort of like a cube here. And we were looking at how water flowed from that cube and the amount of water that flowed through it. So for instance, this might have been delta X and this was A. And there was water flowing through this. So there was some velocity, V. And we could also talk about this area element here having an outward directed A vector, an area vector, and we talked about the flux for this face, this purple face, as being the velocity vector of the water dotted with the area element of this surface. And that was water flow. And it was related to a velocity vector field. At each point in space, the water has some speed and some direction, so it has a velocity. Now, if you looked at all of the faces, you could talk about the flow through the whole thing. And in that, you get a slightly different. For instance, the water comes in over here, and you have an area like this. And I remind you, going back to these dot products, this is the magnitude of V, A, and the cosine of the angle between them. If you forgot about dot products of vectors, go back and review the modules on them. Go back and look at the section we did on work. We're going to need that again here. So in this case, the angle between the blue vector velocity and the purple A was 0, and the cosine of 0 was 1, and so this flux was positive. And it was EA. Over here, however, the velocity arrows are pointing in the opposite direction of A, so the angle is 180. So if we do the same sort of calculation, this is negative flux or negative flow. So the phi over here is minus EA. Up here, A is pointed this way, but V is pointed that away. That angle is 90 degrees. So E dot A is 0. There is no flow across that surface. And we could do the same on the other 4 sides, or the other 3 sides, and we'd find there's no flow there. So there's no flow on 4 of these sides. This side has a minus EA. That side has a positive EA. If we look for the total, that is over the closed surface, 2, 3, 4, 5, and 6 sides. If we looked at all 6 sides, what we would find is that the total flux across all 6 sides is 0. That's because all the water that enters the box leaves the box. Now, I want you to think about that. That's because there's no drain in here where the water gets sucked up, and there's no source that water starts to come from. All the water flows. Water's not created and destroyed out there. And this is a property of the nature, for instance, for these particular things. Now, we're going to want to develop a similar type of thing for flux across a closed surface for electric flux. So let's start by defining electric flux first. It's very similar to the definition we just saw for water flux. The definition, and I'll put an E to remind us we're talking about electric flux, is the electric field, rather than the velocity, dotted again to this area. So we're saying that if you have a surface like this surface, and it has some area vector there pointing out, and you had some electric field right here, that you would find this angle theta, and you would take the magnitude of the electric field times the area at this point times the cosine of that angle. And that would calculate the flux. Now, in water flux, it represented a change in the volume of the water over time. In other words, how much water flowed through the surface in a given time, 10 gallons per minute, or 8 liters per second. What does this electric flux represent? Well, you remember those field line diagrams. The electric flux is a measure. Electric flux is a measure of the number of electric field lines penetrating some surface. Now, I didn't say it's exactly equal to the number. It depends on some constants. So maybe, for instance, one field line represents 10 to the 9th flux. It depends on what you define as how many field lines you're drawing for each coulomb of charge. Did you draw 27 for a coulomb of charge? Did you draw 3? All right, but it's proportional to it. Something else. Remember that the electric field is related to the density of lines. That's number of lines per area. And now you've taken E and multiplied by A. So you got number of lines per area, and you multiply by area. I should say proportional. So naturally it's now proportional to number of lines. So if you have twice the flux, you have twice the lines. Now what is this saying? This is saying that if you have something like this, and you had a set of lines coming out of here, maybe that's a 6 coulomb charge, and over here somewhere in a different problem you had a 3 coulomb charge. So and you were to look at some sort of fixed surface, and does not depend on the shape that you put. Then the flux for this one, which I'll call number 1, divided by the flux, which over here I'll call number 2, is the number of lines here, 6, divided by the number of lines there, 3. There is twice as many field lines here crossing the surface of my green box as there is crossing the surface of this rectangular box. Even though the calculations of the electric field may be different and the areas are different, if you just talk about flux, you're talking about line number. Twice as many lines left here as left there. Okay? Now you can also get a difference in sign. If this had been negative and they'd been coming in, this would have been negative flux. The lines would have been flowing in, not out. Remember, positive is out. Negative is flowing in. All right, we want to find this sort of thing, and you can probably see that it's interesting that the number of lines, of course, we said is related to the charge. So in my case, when I build a closed surface, there's a relation to the ratio of the charge to this ratio of flux. We want to be able to build a statement about flux and the charge inside of your shape. This is called Gauss's law, and this is what we will be dealing with in a later video. All right, that's for this video. We'll come back and finish our discussion of flux in the next video.